So in this video, we introduced the Riemann integral, which is the main integration theory used in this class. I'll mention that in the previous video, I made up a sort of simplified version of the Riemann integral. It's not in the lecture notes. It's very similar to what we're going to be doing today, but with slightly lighter notation. So you might want to take a look at that first. All right, onwards with the new notation for the Riemann integral. I define a partition P of the interval AB to just be a sequence of points x0 strictly less than x1, strictly less than x2, dot, 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 strictly less than xn, with endpoints xn is b and x0 equal to a. Next, for a bounded function f from the interval ab to r and a partition P of the same interval ab, I define upper and lower integrals according to these two functions here. Now, you can look at the equations here, but it's sometimes easier to think about the pictures here, and I'll say what's going on here. Here I've pictured a function f, which is this black curve, and a partition into n equals 7 parts. So x0 is here, x1 is here, x2 is there, x3, x4, x5, x6, and x7. And then I've drawn two functions, a function in blue and a function in green. Now, both of those are piecewise constant functions, and you'll see, in fact, that, well, at least if my picture were perfect, they would be constant on each part of the partition. That is from x0 to x1, from x1 to x2, and so on and so forth. What are these functions, which I've denoted flp and fup? Well, flp on the interval from x0 to x1 takes a value that is the smallest value of f, that is the infimum of f, on the interval from x0 to x1. Now, in this case, of course, f is a continuous function because they're easier to draw, so it's just this minimizing point there. I'm not assuming at this point that f is actually continuous, though, so of course it's quite possible to have jump discontinuities all over the place here. All right, but that's the basic picture for every interval from xi to xi plus 1. To get this function flp for x in that interval, you just look at the smallest value of f on that interval. And so in particular, the one really important feature of this blue curve is that everywhere it's below the black curve, okay? The green curve is sort of the obvious function that's above f. That is, for every interval, the green curve takes the biggest value, or rather the supremum of f on the same interval. So that's what I've written here. I have this supremum, this infimum, and so on. So that's defining my functions green and blue. And then this upper and lower bound on the integral, well, that's just the obvious area of the green and blue curves. So that is, I know, because the blue curve is just a union of a bunch of rectangles, what the area under the blue curve is, and it's given by this formula here. Similarly, the green curve gives me a bunch of rectangles, and the area under the green curve, oops, sorry, I've switched it, the area under the green curve is this, and the area under the blue curve is this thing here, okay? So that's what's going on here. You can look at the formulas as well, but the picture is a perfectly adequate description of what's going on in this particular situation. Okay, now I'm going to make one informal observation. I haven't defined what the integral of f is, but certainly the integral of f should be sort of the area underneath the curve, and we can see here the blue curve is everywhere below the black curve, so certainly the area under the blue curve had better be less than the area under the black curve, if we have any sensible theory of integration. And similarly, the green curve is pointwise above the black curve, so the area under the green curve had better be bigger than the area under the black curve. We're going to continue and make a really important observation relating these upper and lower functions for different partitions. So here's the idea. If I have two partitions P and Q, and P is a subset of Q, all right, what does that really mean? Well, I can have a partition P, say x0, x1, all the way up to xn. What does Q look like? Well, it starts off at x0, maybe it has x1, then it adds in some new point, say y1, y2, before getting to x2, and so on and so forth. That is, it contains every element of P, but maybe it throws in some other elements as well. All right, so that's the situation. So Q is a bigger partition. We often will also say that Q is a finer partition because it chops the interval up into smaller pieces, and P is a coarser partition because it chops the interval up into larger pieces. So when that happens, we have three inequalities between the various lower and upper functions. So L of Fp is less than L of Fq is less than U of Fq, which is less than U of Fp. And the really nice thing here is that the bounds for the finer partition, the better one, get sort of sandwiched by the bounds for the coarser partition. So as our partition gets finer and finer and finer, our bounds sort of get squished inwards. That's what this theorem is telling us. So if you look in the lecture notes, so the proof of this theorem, which uses a bunch of notation and writes everything down very carefully. And certainly it's not a bad idea to be able to do that. Having said that, integration theory is one of those subjects that you can really understand quite well by looking at pictures. So I'm going to give a proof by picture, which can be extended out into a proof by characters. Actually, it's essentially the same proof as is in the lecture notes, but which I think is probably a little bit easier to understand quickly via video, and at least if you're anything like me, is going to be a lot easier to keep in the back of your head than a purely algebraic proof or sort of written character proof. So here's the idea. I have this partition P, the coarser partition at the beginning, and I'll notice that I'm comparing these L things and these Q things, which are sums of, well, the length of the interval times the value of some function over that interval. And since we're comparing sums, and these are really finite sums, right, even for P and Q are both going to be finite objects, if we want to compare the sums, it's enough to compare the terms individually. That is, the sort of term corresponding to I equals 1, the term corresponding to I equals 2, and so on and so forth, right? If we can get a comparison for every term, then certainly we have a comparison for the sum of the terms. So I'm going to do that. I'm just going to zoom in on two adjacent points, xk and xk plus 1, in the partition P. And so here's my picture. I've drawn the function f in black. I have my left-hand point of this part of the partition xk, my right-hand point xk plus 1, and then I've thrown in one point y that's in Q but not in P. Now, of course, I haven't said anything about really how many points are in Q are in here. You could have many points, not just one, but it's not going to change the following argument in any substantial way, and it makes the picture a lot harder to read, so I just drew 1 point. And then I'm going to do the same thing that I did when introducing these lower and upper bound functions as before. I'm going to draw this f sub up and this f sub lp. So in particular, I have this red curve f sub up, and you can check for yourself that this curve is sort of accurate, right? So f sub up on this interval is going to be the supremum of f on that interval. So you can see here's where the supremum happens, and the red curve is just equal to that everywhere. Next, I have this green curve f sub uq, and it's almost the same thing. It's going to be the supremum of f on some interval, but it's not going to be the supremum of f over the whole interval. It's going to take the supremum of f between xk and y over here, which is what's going on. And then after that, it's going to take the supremum of f between y and xk plus 1, which is what's happening up here. And so you can see what's going on. In this part of the interval, fuq is the same, but in this part of the interval, it's smaller. And you can, I think, convince yourself pretty quickly that this is generic, right? I'm looking at, when I'm looking at fuq, the supremum of a function over a smaller part of the interval, and therefore that supremum is going to get smaller, right? Supremums over smaller sets always get smaller. Okay, you can also just see it visually. FLQ and FLP have the same idea. FLQ is the is the infimum of f over these different regions. So it's equal to this curve over here on the left, and then on the right it jumps up. And FLP is the infimum of f over this whole region from xk to xk plus 1. So it's this purple curve way at the bottom. And so the thing that we notice is that actually point-wise, FUP is bigger than FUQ, is bigger than FLQ, is bigger than FLP. And so since we have pointwise comparisons, obviously we have the same comparison for the areas. So that is, we get this thing up here, which is exactly the same ordering of the functions. Okay, so that's a picture proof. I haven't done any sort of algebra in there, but in fact you can expand it, and if you've seen the lecture notes, this is exactly the picture that's being used. Okay. With that out of the way, it makes sense to talk about the Riemann integral and introduce the main definition. We say that a bounded function f from an interval a, b to r is Riemann integrable if the supremum of my lower bounds is equal to the infimum of my upper bounds, where the infimum and supremum are taken over all partitions of AB, or all finite partitions of the interval AB. And when you have that, when these two things, the supremum of the lower bounds is equal to the infimum of the upper bounds, those two things have one value, and that value is the thing that we call the Riemann integral of f from the interval from a to b. Okay. Very similar to what we looked at before in the last video, except in this case, I've allowed any partition instead of the very particular sequence of partitions that I was looking at there. We have a couple of conventions that go along with this. We say the integral from a to a is always 0, and the integral from b to a, if a is less than b, is just minus the integral from a to b. That's just going to make our formulas a lot easier to write down. Okay, so that's our definition, but it's not yet clear that very much is actually integrable. So I'm not going to go very far into that in this video. We'll see a little bit next, but I wanted to at least point out that we can deal with something that we couldn't deal with before. In particular, we can deal with isolated discontinuity. So here's a sort of silly example. I have a function f of x, which is 1 almost everywhere, except at 3 particular values of x, where it takes the value 3. I want to say, hey, what's the integral from 0 to 20 of f of x dx? Okay, so I think we can all guess, right? The integral has to be 20, right? Because f is basically 1 everywhere. And really the point of the exercise is to figure out, so how do you check that sort of obvious fact really quickly using the theory of Riemann integration? And actually the nice thing is that it is actually very quick to check, even though the definition is sort of complicated. And the idea, I hope, is sort of clear, right? We have these 3 bad points, which I've drawn, right? 1, 12, and 19. And what we want is for our lower and upper bound functions to sort of basically ignore those points as much as possible. So what is our partition going to do? Well, we're going to consider the partition Pn, which goes from 0 to 1 minus 1 over n, so just before the first bad point, and then starts again at 1 plus 1 over n, so just after that bad point, and continues on until just before the next bad point, and just after the next bad point, and so on and so forth. Why did I write down this partition besides the fact that it's going to work in the next couple of seconds? Well, what are we doing here? There are a couple of points that we know are not going to contribute to the integral, right? Of course they're not going to contribute. And so what the partition does is it sort of isolates them, right? It sort of chunks them off into these little bits where they're not going to matter when we're doing our upper and lower bounds. Okay, so let's check how that actually works out. Well, L of fpn, this lower function, is really easy to calculate, right? Because the lower bound is just 1 everywhere. It's this black curve. So this integral, the integral of 1 from 0 to 20, of course, is 20. The upper function, u of fpn, is this blue part of the curve. I'll draw in the rest of it. Sort of 1 for a while, and then it jumps up for that little region. 1 for a while, jumps up for that little region, and 1 for a while, jumps up for that region, and is 1 for a while. So it's 1 essentially everywhere except for these 3 little regions of width each 2 over n. And so the area under the blue curve is 20 plus 3 times 6 over n, which converges down to 20 as n goes to infinity. So what have we checked? Well, let's put all of this information together. 20 is equal to L of fpn, that's what we computed here, which is certainly less than the supremum of L of fp over all partitions, right? If we find any partition, that's a lower bound on the supremum. The infn of u of fpn is 20, which is certainly an upper bound on the infimum over all partitions, right? We have a sequence of partitions which has some value 20, and so certainly the infimum over all partitions has to be less than that. And then these two things here are the values that we're interested in when computing the Riemann integral. And so we have a lower bound of 20, we have an upper bound of 20, and so those two things have to both be equal to each other and have to be equal to 20. Okay, that's it, right? So we have to work with a little bit of machinery when doing Riemann integrals, but actually it's not too bad. And you can see that actually understanding the picture really helps, right? If we know what the functions are, we can choose a good partition to work fairly well. We also saw that even though we're taking a supremum over tons of possible things here, actually that added generality doesn't make life harder for us. That added generality makes life easy for us by letting us have a lot of flexibility in the weird sort of partition that we might want to choose. And in particular, customizing a partition for what we know about a function. This idea that sort of having this flexibility in the partition helps us gives us the following general theorem almost immediately. Theorem is as follows. F is integrable if it meets the following criterion. For every epsilon greater than 0, there exists a partition Q that satisfies this inequality. U of fq is less than L of fq plus epsilon. Why is that true? Well, we're just going to repeat this sandwich inequality here, except of course we don't have the 20 on either side. So that is, we have L of fq is certainly less than the supremum of L of fp's, right? Of course, we have a particular partition is less than the supremum for all partitions. By the first theorem that we wrote down, L of fp is always less than U of fp. So this supremum of the lower bounds is less than the supremum of the upper bounds, which of course is less than the upper bound for particular partition Q. And then by this assumption is less than L of fq plus epsilon. So what have we done? We've sandwiched the thing that we're interested in here by a number and the same number plus epsilon. So that means that 0 is less than the difference here, which is strictly less than epsilon for all epsilon greater than 0, and therefore this difference, in fact, has to be exactly equal to 0. Okay, that's a very nice condition that we're going to be using fairly frequently. And as an immediate corollary, we find that all continuous functions are Riemann integrable. And in fact, we already proved it last video, and we just as a quick reminder, the partition that we used was Pn being uniform partition into n parts. Okay, so you can go back where we check that continuous functions are integrable according to sort of the simple theory of partitions in the last video, and you'll see that if a function was integrable there, it's Riemann integrable as well using this criterion. Okay. So that's it. We've now introduced a general notion of integrability, and one nice thing that we have is that all continuous functions are integrable. And furthermore, there are a bunch of functions like this one which aren't continuous, but which are nonetheless integrable. In the next few videos, we'll talk about more general theory about how to get lots of other integrals out of simple integrals. Thanks.